In this course, we're building a totally modular asteroid game in Godot 4.4.1, where everything from the player ship to the weapons and even the asteroids are made up of small reusable components that you can mix, match, and even expand. If you've made it this far, you've got the basics down. A player ship with movement and even shooting. Now it's time to bring the actual asteroids in the game. Because, it won't be much of an asteroid game without them. In this part, we will create the asteroids using composition. We will make a modular system that will allow us to easily create multiple asteroid types. We will also look at using composition to break bigger asteroids into smaller parts, and also hook up a scoring system so that the player gets points for destroying the asteroids. And of course, we'll build a simple UI to show that score on screen. We will also look at a game over screen and a start screen as well. And just like before, everything will be broken down into reusable composable parts. No bloated scripts, no tangled mess. And as always, you can use the timestamps to jump around the video if you're looking for something specific. Let's blast in and start breaking up some space rocks. Let's take a look at the way the asteroids will work. There will be 3 types of asteroids. The big asteroid that breaks into 3 smaller asteroids when hit, a medium asteroid that breaks into 2 smaller asteroids, and a small asteroid that just gets destroyed when hit. Let's make the asteroid. This will be really similar to the player character we made in part 1. So I will be going just a little faster with the explanation here, because I already covered this in great detail in part 1 of the tutorial. That being said, it's still really easy to follow on. We will use an asteroid with an asteroid.gd script attached to it. This script will expect an asteroid behavior class, which in turn looks for a process behavior function, which will handle the individual behaviors of the asteroids. We will use a character body 2D node as we did for the player, and as children of this node, a sprite 2D node to display the asteroid sprite, and a collision shape 2D node to detect collisions. We will also use an empty node for the asteroid behavior, attached a script to it, and empty nodes for the individual behaviors of the asteroids, that being rotation and movement. And later on, we will set up hit detection with a node 2D. Now let's take a look at the asteroid script. We will use an exported variable called behavior and assign it to be of type asteroid behavior. We also get an onReady reference to the asteroid sprite. In the physics process function, we look in this behavior class for its physics process function. And lastly, call move and collide and pass in the velocity, just as we did for the player in part 1. In the asteroids behavior script, we assign a class name asteroids behavior. And in the physics process function that the asteroid script is looking for, we use a for loop to check all the children of the asteroid's behavior node and check if it has the method process behavior. Then call that process behavior function. The process behavior function will hold all the logic that controls the behavior of the asteroids, like moving and rotating. And that's the way composition will work here in a nutshell. Okay, didn't get that? Well, let's break it down. Imagine an asteroid is like a walnut shell. Its main outer layer, the thing you actually see floating in space on its own, is just a shape. It doesn't spin or break apart or do anything fancy. Inside that shell, we can place different kernels. Each kernel is a separate ability or behavior. One kernel might be the rotate ability, telling the asteroid to rotate. Another kernel might be the move ability, telling it how to move through space. And yet another ability, the break apart ability, telling it how to split into smaller pieces when it gets destroyed. Because the walnut shell just listens to whatever kernels are inside, we can mix and match to make all different kinds of asteroids. A big asteroid with rotate and break apart, or a small asteroid with move and rotate only. We never have to rewrite the shell itself. We just change the kernels we put inside. That's the magic of composition. The asteroid's abilities are like removable parts. So we can build endless variations from the same simple shell. Let's take a look at our first ability, the movement ability. We add an empty node as a child of the asteroid behavior node, call it asteroid movement, and add a script to it. Now let's take a look at this movement script. We need an exported variable for a speed range, so that the asteroid can move at different speeds when they're spawned into the game. Next, we set an exported variable for the asteroid that expects a character body 2D. This is going to be the asteroid that's controlled by the script. Then we create variables for direction and speed and set them equal to 0. In the ready function, we set a random direction for the asteroid by starting with vector2.right, which points to the right, and rotating it by a random angle between 0 and tau, where tau is equal to 2 pi or a full circle in radians. This gives us a random direction in any possible angle. We also set the asteroid's speed by picking a random value between the x and y values in the speed range, which define the minimum and maximum speed. In the process behavior function, we move the asteroids by setting its velocity. The direction was already randomly chosen earlier, and we multiply it by the speed to control how fast and in what direction the asteroid moves. After that, we use a wraparound effect so that the asteroid doesn't get stuck off screen. We get the asteroid's current position and the size of the screen or viewport, and we use the wrap F function to check if the asteroid has moved past the screen edges. If it has, it wraps around to the other side. We did something similar for the player movement in part 1. The buffer, in this case 15.0, adds a little leeway to the asteroids, so it can slightly move off screen before it wraps. This prevents it from suddenly disappearing the moment it touches the edge of the screen, making the movement feel smoother. To set up the rotation behavior, we add an empty node as a child of the asteroid behavior node and call it asteroid rotation, and add a script to it. This script adds rotation behavior to the asteroid. Instead of handling the rotation in the main asteroid script, it's cleanly separated into its own behavior. In the ready function, we set a random rotation speed by picking a value between the rotation range.x and rotation range.y. These values are in radians per second, so they control how fast and in which direction the asteroid rotates. A positive value means the rotation will be clockwise, and a negative value means it will rotate counterclockwise. Then, in the process behavior delta function, we apply that rotation by adding the rotation speed scaled by delta to the asteroid's current rotation. Multiplying by delta ensures that the rotation is frame rate independent, so it behaves consistently no matter how fast the game is running. Now that we have the asteroid's movement and rotation done, let's take a look at what happens when the asteroid is hit by a shot. For this, we will use a node 2D and rename it to asteroids hit. We will not use an empty node because we will need to know the position on the screen where the asteroid was hit. Then we add an area 2D node as a child of the asteroid and call it hitbox, and add a collision polygon 2D as a child of the hitbox. Now, the shape of the collision polygon does not really matter at this point, because we will need to adjust it to be the same shape as each of the asteroids we added to. Not to worry, more on this later. And for the score logic, we can simply use an empty node because the score is not dependent on the position. Now, all we need to do is just add scripts to the asteroid hit and score logic nodes. So what's actually going to happen when the asteroid gets hit? Well, if it's a big asteroid, we want it to break into a number of medium-sized asteroids. If it's a medium asteroid, we'll break it into small asteroids. And if it's a small asteroid, we'll just destroy it. To achieve this effect, we will just destroy the asteroid that was hit by a shot and then spawn in the appropriate sized asteroid, be it medium or small. Now let's take a closer look at the asteroid's hit script. First, the @export var spawn and destroyed array will create an empty array in the editor where we can drag scenes like the smaller asteroids that should be spawned when this asteroid gets destroyed. Then we create an @export var hitbox area that expects an area 2D. This will let us assign the specific hitbox of the asteroid that we want to detect the hit or collision with the shot. The next line grabs the parent node of this script, in this case the asteroid itself. This lets the script talk to the asteroid it's attached to. This line here is really useful in that it sets an onReady variable called scoreLogic and checks if the asteroid has a child named scoreLogic. If it does, it saves a reference to it. The scoreLogic node will be in charge of giving the player points when the asteroid is destroyed. The function ready runs automatically when the scene is loaded, and the node is added to the scene tree. Then we check if there is a hitbox area, and if we have a reference to something called hitbox area and area 2D, we can manually connect to the signals area entered and body entered specific functions in the script. Area entered.connect on hitbox area entered, which will check whether the area 2D enters a hitbox, then call the onHitbox area entered function, and body entered.connect on hitbox body entered, which will check whenever a physics body, like a player, enters the hitbox, then call the onHitbox body entered function. I have an entire video dedicated to signals and how to set them up, so please check it out if you want to get a more detailed explanation of how signals work. When you're done here, signals are like doorbells. When someone presses them, an event happens. Your chosen function immediately answers the door. We're using the area 2D signals here, so the hitbox doesn't have to constantly check what's touching it. Instead, it just sits and waits. And when something enters, Godot automatically rings the bell by triggering the connected function. This keeps our code efficient and organized. Each function only runs exactly when its events happens. It also makes the hitbox self-contained. We can drop it into any scene and it will instantly be able to respond to objects entering without needing extra setup in the main game loop. The function onHitbox body entered will run when a physics body, like the player, collides with the asteroid. Because in part 1 of the video we added the player to a group called player, we can now check if the object is in the player group. And if it is, remove the player by calling queueFree. Similarly, function onHitbox area entered runs when another area enters the asteroid's hitbox, like the shot. It checks if the object is in the shots group, meaning it's the player's projectile, and if it is, spawns smaller asteroids using the spawnChildren function, then tells the scoreLogic to award points if that node exists, and lastly, removes the asteroids and the shot from the game using queueFree. Function spawnChildren runs when the asteroid gets destroyed. It loops through all the scenes in the spawn on destroy array. For each one, it creates a copy of that scene using instantiate and places that new object at the same position as the original asteroid. And finally, it adds it to the scene using callDeferred. This safely delays adding the new objects until Godot is ready. Now let's take a look at handling the score in the game. I'll break this down into two parts, the scoreLogic and the UI to display the score. First, the scoreLogic. This is where I will need to break the composition rule a little and create a centralized system to manage the score by using an autoload. An autoload in Godot is a script or scene that is always loaded and stays in memory throughout the entire game. It is really useful for things like managing global data, in this case, the score, or emitting signals across different scenes. We'll look at that next. First, we make a new folder called Autoloads and create a script called Score Manager. Then, in the project settings, under the global tabs, we browse to add the Score Manager script. Then click Add to add the Score Manager script. The Score Manager script stores a variable score as an integer and sets it equal to 0. Then we will make a function add score that takes a score value also as an integer. To add the score, all we do is add this score value to the score, and for now we can just print the score to the console so we can see that it's working. The score logic script will be very simple. We just create an exported variable for score value as an int that we can assign any value to for the asteroid that we want to add a score value to, and we make the award score function that we called in the onHitbox area entered function mentioned before. All this function does is gets the score manager autoload and calls the add score function and passes in the score value. And just like that, when we destroy the asteroid, we can see that the score is being printed in the console. So now we got the score being printed in the console. Let's display it on screen and update it every time the asteroid gets destroyed. To do this, we will need to use Godot's powerful UI system. In the game scene that we created in part 1 of the video, we will add a canvas layer node. A canvas layer node in Godot is a special node that lets you draw UI or 2D elements on a separate layer from the main game world. This means everything inside the canvas layer will always stay on top of your game scene, unaffected by the camera or scrolling, making it perfect for things like HUDs, score displays, health bars, or menus. The other node that we will add is a control node. A control node in Godot is the base node for all user interface elements, like buttons, labels, and panels. It provides built-in features for handling things such as size, anchors, margins, and alignment, which makes it easy to position and scale UI elements across different screen sizes. Since most UI nodes inherit from control, it's the foundation for creating menus, HUDs, and other interactive interface elements in a game. Then I will use a label node. A label node in Godot is used to display text on the screen and will work great for showing things like messages or instructions in the game. And I can change its properties like its font, color, size, and alignment. Since a label is purely for displaying text, players can't interact with it, making it perfect for static information in the UI. Then I add a script to the label node. Before we take a look at the script, let's adjust its properties. First, with the container node selected, we can change its anchor presets to full rect. Then, with the label node selected, we can change its anchor preset to top right. What this does is make sure that it is anchored to the top right. So no matter how the screen changes, the label will be at the top right of the screen. Now over in the inspector, let's add some zeros to the text box to represent the score so we can see how it looks. Remember I said that we can change the properties of the label? Well, one way to do that is down here in the theme overrides. We can change things like the color, the font size, and other settings. But there is a better way we can do this to make things more consistent throughout the game. Godot 4.4.1 has label settings, and we can use these to make settings that we can use for all the labels in the game. We just click the drop-down arrow and click New Label Settings. Then we can adjust various properties like the font, the size, the color, and even add an outline. Once we're satisfied with the settings, we can click the drop-down arrow again and save the settings as a .tres file. And now we are able to use these exact settings on other label nodes in the game. Now let's take a look at how we can update this score label to show the score value. First, we can go to the score manager autoload. And remember I said that we can use this to emit signals as well? We can create our own custom signal called score updated by using the signal keyword. And now every time we call the add score function, we can also emit the score updated signal. Now over in the score label script, we can add an @onReady reference to the score label. And in the ready function, we can set the score label.text equal to the string value of the score manager score. Now, there are a number of interesting things happening here. This line updates the text of a label node so that it shows the player's current score. ScoreLabel.text grabs the text of the score label, and ScoreManager.score is the score variable stored in the score manager. The str converts that number into text, since labels can only display strings. By doing this, the label on screen shows the latest score value from the game when the game first starts. This next line connects the score updated signal from the score manager to the function onScoreUpdated. It means that whenever the score changes and the score updated signal is emitted, the onScoreUpdated function will automatically run. The onScoreUpdated function just repeats the same line in ready to update the score text. This way, the game reacts instantly to score changes without constantly checking for updates. Now, when we play the game, we can see that the score automatically updates when the asteroids are destroyed. So far, we've been working on creating one asteroid, right? But remember, there are 3 types of asteroids in the game, and I have not really made it clear as to which one we're working on. So let's take a look at that now. You see, the way I've set out to explain composition here is by creating a base asteroid scene, if you want to call it that, and use this base scene to create other asteroids, medium and small. To do this, Godot makes it really easy. We can take advantage of Godot's ability to save branch as scene, which, as the name states, saves any branch of the scene tree as a new scene. And make local, which allows you to take any scene that is used in the scene tree and make it local to the scene tree, exposing all its nodes. So far, we've made our asteroid and assigned it its behavior in terms of movement and rotation. We've also set up hit detection and how to handle scoring. So now let's jump into saving these scenes as reusable paths. All we need to do is just right-click on the node we want to save and hold on. We can't just save every branch as a new scene and expect things to go smoothly. There are a few things to consider. While doing research for this tutorial, I found this in the Godot documentation. Reusing the scene in multiple places creates issues because node paths don't find their targets and signal connections established in the editor break. You must instantiate the subscenes without them requiring details about their environment. You need to be able to trust that the subscene will create itself without being picky about how it's used. And this warning, you should favor keeping data in-house, internal to a scene, as placing a dependency on an external context, even a loosely coupled one, still means that the node will expect something in its environment to be true. This is all just fancy talk to mean each scene you create should mind their own business, but also be able to communicate with other nodes and scenes in the main tree, kind of like the perfect neighbor. To avoid this, we make sure our reusable scenes can work on their own, no matter where we use them. They shouldn't care what their parent is or what's around them. That way, we can just drop them into our game and they'll behave just the same. We'll keep everything our scene needs itself. If it relies on something outside, like expecting a certain variable or another node to be present, that can be risky, even if that connection is loose. The scene is still assuming that the outside world looks a certain way. That makes it harder to reuse or move around. But not to worry, we will address that. Oh, and I will put a link in the description to the documentation. It's a really interesting read, and I urge you to check it out. So here I have the main asteroid that we've been working on. Before we get started, let's change the background color from gray to black. We go to Project, Project Settings, and under the environment, we can change the default clear color to black. Next, let's create a folder for the asteroids. In the Scenes folder, we can right-click, create new folder, and call it Master Asteroids. Next, let's create another folder for the asteroid behaviors. And we can save the asteroid behaviors as separate scenes. We right-click, select Save Branch as Scene, and save it in the folder. We can see that a scene icon is displayed next to the node. Let's do the same for the asteroid rotation. We'll do the same for the asteroid hit and score logic, but we will leave the hitbox to be part of this master asteroid. Then we just rename the asteroid to Asteroid Master. And now we can remove the scenes that we saved from this master asteroid. And lastly, we will save the Asteroid Master as its own scene. We just go to Scene, Save Scene As, and choose where we're going to save the scene. Then rename it to Asteroid Master. Let's run this scene to see what happens. First, I'll bring the asteroid towards the middle of the screen so we can see it more clearly. Then we click Run Current Scene. We can see that the asteroid just floats on the screen, and it really doesn't do anything. So now let's fix that. Let's start by making this small asteroid. The first thing we'll do is change the sprite. We select the asteroid sprite and drag the new sprite into the sprite texture in the inspector. Now we will need to adjust the collision polygon. And we should also adjust the asteroid collision. Next, we can add some behaviors to the asteroid. And to do this is really simple. All we need to do is go to the asteroid scenes that we just created for the asteroid behavior and drag the behaviors we want into the asteroid. First, movement and rotation will go in as children of the asteroid behavior. We will need to assign the asteroid in the inspector. Next, we will assign the asteroid hit and the score logic. The asteroid hit will be assigned as a child of the asteroid master and also the score logic. We will need to assign the hitbox area to the asteroid hit. We simply click to assign and select the hitbox. We will not be spawning any asteroids when this asteroid is destroyed, so we do not need to change anything in the array. Let's now assign a score value to the small asteroid. I will set it to 50. For the asteroid movement and rotation, we can actually increase the speed range. I will change the speed range to between 2 and 3.5. Now I can move the asteroid again to the middle of the screen so we can test this out. And run the current scene. Okay, I'm happy with that. It's not recommended to change the transform of a root scene, so let's undo that transform. Now we can rename the root scene to Asteroid Small and save the scene. And that's it. The small asteroid is done. Let's now make the medium asteroid. We open the master asteroid and save the scene as medium asteroid. Then we rename the root node to Asteroid Medium. And repeat the process of bringing in the behaviors we want. Then we change the sprite. And adjust the collision polygon. We can adjust the speed range. And assign the asteroid. The only difference here is in the asteroid hit. In addition to the hitbox, we will also need to assign the asteroids in the asteroid array that will be spawned. For the medium asteroid, I will just spawn 2 small asteroids. By now, you should have an idea of what we're doing. For the big asteroid, I did the exact same as I did for the medium asteroid. I just added the big asteroid sprite, adjust the collision shape, set the asteroid behavior, score logic, and for the asteroid hit, spawned in 3 medium asteroids. Now that we've added the asteroids, let's create a simple start screen. With the canvas layer selected, we click the plus to add a new node and search for a control node. Let's rename the control node to start screen and change its anchor presets to full rect. Next, we add a panel node and change its anchor presets to full rect. To the panel node, we can add another label node. Let's rename this to Start Text and add some instructions for the player. Now here's where the label settings come in handy. We can click on the empty label settings, choose Quick Load, and choose the label settings we saved earlier. We will use this as the base of our new label settings. Now we just change the anchor presets to center, and we can change the horizontal alignment to center. Now let's make these settings unique, and we can also save these label settings. I will save it as label settings 1. Next, we add a texture button to the panel and rename it to Start Button. Then I drag in the texture for the normal setting. We can change the stretch mode to Scale. Then we add a label node as a child of the button. Rename it to Start Button Text. Add the text and choose the label settings 1. We can change the anchor presets of the Start Button text to center and change the anchor presets of the Start Button to center as well. Then we can move it down a little. There's just one last thing I'll need to do. Since I plan to start the game paused, with the Start button selected, I'll need to go to the inspector, scroll down to the Node section, and change the process mode from Inherit to When Paused. And that's it for the start screen. The easiest way to make the Game Over screen will be to duplicate the start screen and make some minor changes. To do this, we right-click, choose Duplicate, and for now, let's hide the start screen. Now we can rename the control node to Game Over. Change the start text to Game Over. Rename the label to Game Over Text. And change the start button to Game Over button. Then we add a script to this canvas layer, and let's look at some code. I created a game manager script and added it to the autoloads. The game manager autoload is really simple. It just has 2 signals, the game started signal and the game ended signal. The canvas layer script controls what screen is shown when the game starts and at game over. First, we get onReady variables for the start screen and the game over screen. Then, in the ready function, we connect to the game started and game ended signals in the game manager and called onGameStarted and onGameEnded functions. And lastly, we emit the GameStarted signal. The onGameStarted function simply gets the tree and sets paused to true, which pauses the game, and then shows the start screen using Godot's built-in show function. The onGameEnded function also gets the tree and pauses the game. However, it shows the game over screen instead using Godot's built-in show function. So where do we emit the game ended signal? The best place to do this is when the asteroid hits the player. In the onHitbox body entered signal, we can call GameManager.GameEnded.emit so that the canvas layer script will know that the game has ended. Now all we need to do is connect on-press signals for the start button and the game over button. To do this, we click on the start button, and in the Node tab, we select Pressed, then Connect, and connect it to the canvas layer script. Similarly, for the Game Over button, we select the Game Over button, and in the signal, select Pressed, and connect it to the canvas layer script. Now we can see the On Start button pressed and On Game Over button pressed signals created. The On Start button pressed signal will simply get the tree and set pause to false to unpause the game, and then hide the start screen by using the built-in hide function. The onGameOver button pressed function will simply restart the game by getting the tree and then reloading the current scene, and reset the score manager's score to 0. Now when we run the game, we have functioning start and game over scenes, but the game loop is still not complete. We need to spawn in the asteroids automatically in the game. So let's make a really simple asteroid spawner. In keeping with the theme of composition, we will create an asteroid spawner scene that we can simply drop into the game. We will use a node 2D as the root node and use an array of marker 2D nodes for the position that we can set in the inspector. We also want a random asteroid to spawn in at a random marker position chosen. So to do this, we will use an array of asteroids that we can also assign in the inspector. Let's take a look at the asteroid spawner script. We will need exported arrays for the asteroid scenes as pack scenes and the asteroid spawn positions as marker 2Ds. Then the exported variables for spawn rate, minimum spawn rate, and difficulty increase, and also variables for the current spawn rate and the time passed. In the ready function, we set the current spawn rate equal to the start spawn rate. Then, in the process delta function, set the time passed plus equal to delta to increase the time passed by delta. If the time passed is greater than or equal to the current spawn rate, we call the spawn asteroid function to spawn in the asteroid, then set the time passed back to 0. Next, we gradually increase the game's difficulty by making the asteroids spawn faster over time, but without letting the spawn rate go below a safe minimum. Let me explain. The current spawn rate is the time delay between spawns, and each time it's updated, we subtract the difficulty increase to make the spawns happen sooner. However, we wrap it in the built-in function max, so the value never goes below minimum spawn rate, ensuring the game doesn't become impossibly fast. In short, it makes the spawning speed up smoothly until it reaches the minimum limit we set. In the spawn asteroid function, we assign a variable asteroid scene to a randomly picked asteroid from the asteroid scenes array, and a variable asteroid that we will instantiate from the asteroid scene. Next, we pick a random position by setting a variable random spawn position equal to a randomly chosen marker 2D from the marker 2D array, and set the asteroid to be spawned global position to be equal to the position of the randomly chosen marker 2D, and then place the asteroid in the scene by getting the tree of the current scene and adding the asteroid as a child. And there you have it. The game loop is complete. In the next video, we'll take a look at spicing things up a bit. I would really love to revisit the spawning system and see how it could be improved. We'll also use composition to create some power-ups and special abilities. A big thanks to all of you that have been following the series so far, and a special shout out to Francis Coromero 232, who had a great suggestion. I'll be honest, I'm not that great with GitHub, so I've created an itch page for the project. with a devlog of sorts, so you can find all the project files on there. So feel free to check it out. Thanks for joining me in this series. If you like what you saw so far, why not subscribe and turn on notifications so you can join me for future updates. And while you're here, why not check out one of my other videos like this one that's kind of like an introduction to how composition and decoupling works in Godot. But you know what? I'd love to hear what you think of the series so far. Until next time, happy coding, and I'll see you in the comments. This has been Diragu Games.